We start with the secular terms. And remember, what we are looking for here are the cosine arguments in the direct part of the disturbing function that are independent of the mean longitudes. That is, cosine arguments that do not contain any lambda terms. If we quickly flip back to our second order expansion of the direct part of the disturbing function, we see that we have several cosine arguments of the form j lambda 3 minus j lambda 2, appearing here and here, for example. If we set j to be equal to 0, then these arguments become independent of the lambdas. This won't work for terms like this, because in this case, we will still have a 1 lambda 2 remaining, or a 2 lambda 2 remaining, and so on. So setting j equal to 0 only gives us these first two sets of terms as our secular terms. Recall also that we are considering the case where I3 is 0, which means that all instances of S3 are set to 0. And so, coming back to the simplified version of this, we are only going to retain this relatively small number of terms, all of which come from those first two cosine terms. The one where we could eliminate cosine entirely, as in here, and the one where the cosine argument only retains var pi 2 minus var pi 3, because the j being set to 0 takes care of the lambda arguments in here. So by flipping back and forth between these two slides, you can see how we got from our infinitely many terms in our second order expansion to this very, very small number of terms. And we are furthermore going to simplify things by defining these coefficients, C0, C1, C2, and C3, that map to the coefficients found on that previous slide. C0 will be just 1/2 the Laplace coefficient B0 of 1/2. C1 will be this whole expression. And recall, the delta operator, d to the n, is defined as the nth derivative in delta, and delta itself is the ratio of the semi-major axis of body 2 to body 3, always under the assumption that A3 is larger than A2, that A3 is an external perturber. So you can see here's where our C0 comes from. We're only retaining the 0th j. Here's where C1 comes from, and so on and so forth. At this point, it is also worth remembering that Rd is just one factor in the actual full disturbing function. Remember that we defined the disturbing function on body 2, R2, as mu3 over A3 times Rd plus mu3 over A3 times our delta, A2 over A3, times this Re, the external perturber indirect part of the disturbing function. However, in this case, Re will have no secular contribution. We can see that by inspection, by noting that there is nothing that we can do to eliminate the lambdas from these cosine arguments. And therefore, there can be no secular contribution from the external perturbation part. Secular contributions, in this case, can only come from the direct part of the disturbing function. And so our full disturbing function, our full perturbing potential in this case, will just be mu3 divided by A3 times this Rd secular expression here. We plug this into our linearized Lagrange planetary equations from the previous slide, and we find that we have 0 variation in the semi-major axis of body 2. We have E2 dot secular being given by this factor times the sine of var pi 2 minus var pi 3. Var pi 2 dot secular has a very similar form. It's a function of cosine of var pi 2 minus var pi 3 plus the factor of 2c1e2, where again, c1 is given by this coefficient here. And omega 2 dot is just c2 mu3 over 2a2 squared a3 n2. And the n2 here is, as usual, the mean motion of body 2. These expressions also take into account a few of the simplifying assumptions that we have made. In particular, we can write the gravitational parameter of body 2's orbit, that is g times the sum of masses m1 plus m2, is equal to a2 cubed times n2 squared. This is just a direct application of Kepler's laws. But in this case, the sum can be approximated as just m1 because m1 is much, much larger than m2. And therefore, the gravitational constant itself can be approximated by a2 cubed times n2 squared over the mass m1. And that means that all instances of mu3, which we are defining in this case as gm3, can be approximated by a2 cubed times n2 squared times the ratio of m3 to m1. We are also going to assume that E2 can be much larger than E3. This conceptually makes some sense, although it does restrict the generality of our analysis. But remember, we are thinking about the case where M2 is a small body that is being perturbed by a much larger body, M3, but that both are in orbit around a much larger body, M1. So again, the conceptual picture here is something like an asteroid or a spacecraft being perturbed by a planetary body in orbit around the sun. Without any loss of generality, we can also take var pi 3 to be 0. Remember that we are setting I3 to be equal to 0, and so we are defining everything with respect to the orbital plane of body 3. That means that var pi 3, which is the sum of omega 3 plus capital omega 3, that is the longitude of the ascending node plus the argument of periapsis of body 3, this is a true angle. Both of those lie in the same plane because the inclination is 0. And we can set the first unit direction of that plane to be a completely arbitrary direction in space, which means that we can set var pi 3 to be 0 without any loss of generality whatsoever. Making all of these assumptions, we can thus integrate these expressions and write these expressions represent the integrals in time of the differential equations given on the previous slides, which were the result of the application of the linearized Lagrange planetary equations to only the secular terms of the disturbing function for body 2. And what they tell us is that the semi-major axis will not change. To first order, we expect no variation in the semi-major axis of body 2. It will retain its initial value for all time. The eccentricity will be given by the initial eccentricity minus the mean motion times the semi-major axis over the rate of change of the longitude of periapsis times the mass ratio of body 3 to body 1 times that C3 coefficient from our disturbing function expression times the eccentricity of body 3, all times the cosine of the initial value of the longitude of periapsis minus the cosine of the current value of the longitude of periapsis. And so we expect overall sinusoidal variations in the eccentricity of this body due to that external M3 perturber. Turning now to the longitude of periapsis and the longitude of the ascending node, both of these have very similar forms. They are their initial values plus mean motion times the delta, that is the semi-major axis ratio of body 2 to body 3, times the mass ratio of body 3 to body 1, times a function of the coefficients of our disturbing function, 2c1 in this case and c2 over 2 in this case, all times time. Both of these represent linear ramps. So this is our prediction. Semi-major axis will stay the same. Eccentricity will vary in some complicated fashion, but will primarily exhibit sinusoidal variations, and both the longitude of periapsis and the longitude of the ascending node will linearly ramp in time. Does it work? The answer is yes, it works shockingly well. Here is a result from Murray and Zermatt. This is figure 6.3 in the Solar System Dynamics textbook. And what this is showing are the predictions of these variational equations shown by the thin black lines. And then the thick black lines, or in this case, the dots, represent the results of numerical integration. The specific system that is being integrated here is the mental picture that I keep coming back to. We have a test particle, an asteroid or a spacecraft in orbit around the sun being perturbed by Jupiter. So the abscissa here is a time axis given in Jovian periods. And you can see that the integration goes out to 20,000 Jovian periods. So we're talking about very, very long-term changes. This is an analysis that is specifically for the natural evolution of mass in the solar system. The semi-major axis variation, as predicted, is tiny. The prediction was 0. It is not going to be exactly 0, because this is only a first-order analysis of only secular terms. Remember just how much information we've thrown away. We've taken an expansion of the disturbing function that contains literally an infinite number of terms, and we've retained 4 of those. Out of everything that is happening, we are just looking at the lowest order terms of just the secular perturbations. And yet, the true variations in major axis is 1 part in 10 to the 6th. So we're talking about tiny, tiny changes. The eccentricity, which we predicted to have a predominantly sinusoidal variation, does exactly that. You can see that the two traces match shockingly well, again, giving how simplified this expression is compared to the full thing. And as expected, both the longitude of periapsis and the longitude of the ascending node are linearly ramping in time. And here you are seeing the 360-degree or 2 pi radian phase ramping that occurs anytime we linearly change an angle. Again, the thin lines are the predictions of these equations, and the thick lines are the numerical integration. They agree to an incredible degree. This analysis has incredible predictive power, with the caveat that this is a specifically crafted example selected such that the secular perturbations are dominant in this system. One final caveat that is buried deep in all of this has to do with these Laplace coefficients. Remember that these are functions of some argument, and in this particular case, they are functions of delta, the semi-major axis ratio of body 2 to body 3. In the numerical evaluation that generated these figures, these Laplace coefficients were evaluated for a single value of delta. This is motivated by the fact that these expressions predict that the semi-major axis of body 2 is not going to be changing, and our incoming assumptions tell us that the semi-major axis of body 3 is similarly not going to be changing because body 2 does not perturb body 3 to any significant amount in the system that we are studying here. The numerical evaluation of the actual variations in major axis backs up that claim and makes it okay to have evaluated the Laplace coefficient for a single fixed value of the delta argument. Before moving on, I want to briefly discuss the numerical evaluation of these coefficients, which is really the numerical evaluation of the Laplace coefficients and their derivatives, in this case, up to second order. There exists an enormous body of literature on the efficient computation of these coefficients, but if we are not particularly concerned about efficiency, one of the simplest things that we can do is to directly implement the expressions given on this slide. Here we've defined 1/2 of the b sub s j Laplace coefficient evaluated on x as this set of products scaled by the factorial of j times x to the j times the hypergeometric function with these specific arguments. And these are all constructs that are built into a variety of high-level languages and various low-level math libraries that are available for essentially any language that you might be working in. We can also take advantage of the fact that b sub s of negative j is the same as b sub s of j. So if we implement this expression with only absolute values of j, then we will cover all possible inputs from negative infinity to infinity. And we can use this set of recursion expressions to calculate the nth order derivatives of the Laplace coefficients. So here is one reference implementation using Python and the SymPy package. And as you can see, what we've done here is just exactly encode the equation given in that slide. We are multiplying everything by 2 because the expression was for 1/2 of the Laplace coefficient. The rising factorial is exactly this set of products. It is divided by the factorial of the absolute value of j, and it is multiplied by x to the absolute value of j, and everything is finally multiplied by the hypergeometric function with arguments s plus the absolute value of j, absolute value of j plus 1, and evaluated on x squared, which is the form given here. We can similarly define the first derivative of the lambda coefficient, and it will be s times the lambda coefficient of s plus 1 j minus 1 x minus twice x the lambda coefficient of s plus 1 j and x plus the lambda coefficient of s plus 1 j plus 1 and x. This is exactly this expression here. Next, we define a lambda function or anonymous function for the second derivative of the Laplace coefficient, which will be s times the first derivative of the Laplace coefficient evaluated at s plus 1 j minus 1 x minus twice x times the first derivative, and so on and so forth. That is a direct application of this relationship given here for n equal to 2. We can run these 3 lambda functions on symbolic inputs just to see what they give us. So the lambda coefficient of sjx is exactly what is shown here. This s to the j here represents that rising factorial, which is written out in the product form here. Here's the first derivative, which gives us a rather horrible looking set of expressions, and the second derivative, which gives an even more horrible looking set of expressions. So as an example, we're going to evaluate the numerical values of the C0, C1, C2, and C3 coefficients associated with the example from Murray and Dermott that we were just looking at. Recall, C0 is 1/2 of the B0 coefficient for 1/2. C1 is 1/8 times the quantity 2 delta times the first derivative of that 0 1/2 coefficient plus delta squared times the second derivative of that same coefficient. C2 is negative 1/2 delta times B 1/3/2, and C3 is 1/4 of 2 minus 2 delta times the first derivative minus delta squared times the second derivative of the B 1/2 1 coefficient. And each of these coefficients has an argument, the x value, the input value of delta, which is the ratio of A2 to A3. Here we define additional functions that wrap our various derivative functions, and they are all numerically evaluating the inputs. So x is expected to be a numerical input in each of these cases. And we are setting the various j and s values as needed. This example that we were looking at just now is described in Murray and Dermott via these parameters. The primes represent the variables associated with body 3, and unprimed values represent parameters associated with body 2. MC is what we've been calling M1, the central body. So M prime over MC is the ratio of M3 to M1, in this case, Sun to Jupiter. The naught values are the initial conditions for body 2. Alpha is A over A prime, and so alpha here is the thing that we've been calling delta. And these are the numerical values as given in the text. We can check these, and we find that we have exactly the same values, just to more decimal places. Murray and Dermott also point out that twice C1 should be equal to negative C2 over 2 in this case. We check this by adding 2C1 with C2 over 2, expecting a 0 value. And what we get is a value of 10 to the negative 18th, which is essentially 0 in this data type. So this is by no means the most efficient way of doing these computations, but it is a relatively straightforward one from an implementation standpoint. And it is leveraging a lot of the machinery using these built-in functions that already exists in Python, and equivalent functionality exists in lots and lots of other languages.